The central essential concept of information theory is that likelier events have less information than rarer ones. So this might not sound intuitive at first, but let's consider an example. If a friend sends a message to you that the sun rose this morning, that has no informational value. Something that happens every single day without fail at the same time or at a predictable time, at least, that has no information content. Whereas if a friend messages you to say that they broke their leg when you were planning to go skiing with them or something like that, that is rare. And so it has a lot of information content. The essential equation of information theory is self-information, which is conveniently a really simple equation. So the self-information of some random variable x is equal to the negative logarithm of the probability of that event x. So this is related to this idea that likelier events have less information content than rarer ones. So we'll code this equation up and we'll work through some real numbers in a hands-on code demo in a moment. But to give you an overview of how this self-information equation works, it quantifies informational content. So if the probability of an event is guaranteed, if it has a probability of 1, that means there's a 100% chance it's going to happen, like the sun rising, then the negative log of 1 comes out to 0. So there's no self-information if that event is guaranteed. The less likely an event, the greater the self-information. And again, we'll look at some examples of this in a hands-on code demo in just a moment. Another key thing to know is that independent events are additive. So if one head flip of a coin has a particular amount of information content, then 2 heads flips has exactly twice that self-information. Let's jump to that hands-on code demo now so you can see self-information in action. All right, so we're back in our subject 5, probability notebook, and we are now in the third and final segment, finally, in this gigantic notebook, so you can make your way there. If it's been a while since you've executed any code in here, then you might need to rerun the preceding cells. Your session in Colab might have timed out, in which case you can just click anywhere around here and run all of the cells before. All right, so recall from the slides that the self-information formula is this here. So the information of some event x is equal to the negative log of the probability of that event. So we can code that up here. We pass into this self-information function the probability, my probability, my p. And we just take the negative log of it. That's all that we return. Simple enough. So as I mentioned on the slides, if we have a probability of 1, there is no information. The information content of an event that is guaranteed, that has a probability of 1, is 0. Now, if the event is less likely, so if there's a 10% chance of it happening, then the self-information is higher. So we see a self-information of 2.3 for an event with a probability of 0.1. And as we get even smaller, so an event here with a probability of 0.01, now our self-information has jumped to 4.6. And as an example of, say, a coin flip of, say, heads has a probability of 0.5 with a fair coin. We've talked about that example a lot in these live lessons. And that particular event with a probability of 0.5 has self-information of about 0.7. And just to reinforce the final point from the slides, that if we have 2 heads flips, each of which has a probability of 0.5, then we can sum up those separate self-information values, and we see that the self-information of those 2 events is twice 0.7, about 1.4. So depending on what logarithm base we use, the units of self-information vary. Most frequently, the units are either nats or bits. So nats are the unit that we use if we're using the natural logarithm, which is actually what we were doing so far in this notebook when we were using the NumPy log method. So that by default is the natural logarithm. And this is most typical in machine learning, which is why I chose to use it in this demo. And yeah, so nats are probably what you would see most often in ML. However, just so that you're aware, there are also bits, and that's when we have a base 2 logarithm. A synonym for bits is Shannon's, named after that father of information theory, Claude Shannon, and this is more typical in computer science. So speaking about this in the proper units now, the self-information of an event with a probability of 0.1 is 2.3 nats. That's what we calculated right here. Nice, so up next we'll get into a little bit more advanced information theory, building on the self-information that we learned about in this video.